Hello everyone, my name is Paulus Bosdinch, and today I'll be presenting our paper about domain-specific languages for deep learning lifecycle data management. The deep learning process is long. The training has many variables you can change, any combination of which have a significant impact on the results. Ideally, you want to be able to track these relationships, save your research progress, have it be reproducible, as well as sharing your discoveries throughout. But tool support is lacking. It's hard to keep track of everything. Deep learning lifecycle data management is needed. Machine learning has a complex lifecycle consisting of many phases and steps, from the preparation of the training and test data, via model development and training, to testing, and finally deployment. Although the machine learning libraries themselves, like scikit-learn, TensorFlow, PyTorch, etc., have already matured in the last few years, the pipeline around them and the corresponding tool landscape is still in development and is very fragmented. Each of the tools covers one or several aspects of model development, and for a complete pipeline, you may need to select the whole rainbow of tools to then be combined. Current state-of-the-art tools are many and varied, each with its own focus, with some even trying to automate parts of machine learning to open it up to non-ML experts. However, these techniques are not mature enough yet, and in many cases developers still have to run the machine learning experiments manually. This involves iterative running of experiments in search for the best model architecture and for the best hyperparameters. Natural requirements here are the ability to track, compare, and reproduce the experiments. Good tool support is essential for development productivity. To this goal, these tools provide a set of library functions for augmenting the training program with the tracking functionality. A natural counterpart then is a tool for visualization and result comparison. From this approach, the closest to ours is Weights&Biases, unfortunately a commercially closed project. It's built to support visualization and comparison of experiment metrics as a dashboard containing tables and charts. Unfortunately, users are limited to the visualizations provided, and though there are many, if something is missing, the tool cannot be extended. You also can't add semantics to row names of logged content, meaning unless Weights&Biases has built-in support for it, you can't have data depictions be determined by the type of data you're logging. So what you end up with is a tool that tries to be all-encompassing, but for most real tasks ends up having tons of unused functionality while not meeting all of your needs. What's missing is an easily usable extension possibility for adapting to a specific deep learning task domain. This situation becomes very similar to the one in the system modeling area. There, the universal modeling language was developed, and naturally this language is very complicated. Typically, for any real tasks, a very small subset of these many possibilities were applicable, while at the same time something was missing for tasks in the given domain. Besides that, in real application domains, there is a desire to obtain software implementation from the chosen language automatically. As a result, the idea of domain-specific languages and tools developed rapidly. Required was not a single universal tool, but a DSL tool-building framework. By using such a platform, an expert of the given problem domain could relatively easily build the required tool themselves. A question then arises. Could a domain-specific language approach not be applied to the deep learning lifecycle data management area as well? In other words, no complicated universal tool, instead a DSL tool-building framework where the deep learning domain expert themselves can build the tool for their specific needs. Here begins our proposed solution. It consists of three parts. A core tool, a simple but more general version of Weights&Biases that is stored on a data server. The core library, which is installed on the workstation of the deep learning expert that sends messages to the data server. And the core extension mechanism, also on the data server, that can extend the bare-bones core tool to great levels of customization. The results and stored information can then be viewed through a website from any device. The website access to the core tool lets you log in and then create and view projects. Let's say you have an image captioning project. You can use the core tool to upload your training and test data, view your runs of the training program, under each seeing your logged hyperparameters, golden guessed captions, accuracy. You can upload the captioned image as a file, loss graphs, as well as checkpoints and code for recoverable progress. And this is just the minimalistic base version. To later extend this tool, we need to reveal some of the inner structure. In purple, you can see the messages that can be sent from the augmented code. These library functionalities won't change, but a flexible role name for logging and file upload ensures universality of the library. In yellow, there's the core logical metamodel, showing how the data is afterwards structured. This is one instance of the core logical metamodel showing how having multiple runs looks with the logged messages and files under them. But the big new thing is the advanced core tool extension mechanism. There are two ways to allow extension. One, reveal the core tool code, but that is complicated for the user as they have to familiarize with too much information. The second option, reveal only the necessary parts, still giving enough understanding of the core platform internals for extension. What we have to reveal is the repository structure, the logical metamodel, and the Mongo database structure. The repository structure can be seen here. It has a root folder log platform, inside which the whole core platform software is contained. Encapsulation like this is important, so if the system is to be sold, you just transfer this root folder. Second is the logical metamodel we already encountered earlier. Lastly, the Mongo database structure, within which the logical metamodel and its instances are stored. Here you can see a side-by-side of a metamodel instance and its depiction in the Mongo database. Now, the Metamodel specialization used has been developed by the authors in previous papers listed here. Roughly, we allow some classes and associations of the universal metamodel to have subclasses defined. In the compressed notation, you can see an example of a business trip specialization from a simple workflow universal model. So to back up, we first need a universal metamodel for a domain, the domain here being deep learning lifecycle data management. We can then define a specialized metamodel for each use case in the domain, meaning have a custom version of the tool for each deep learning project to fit its specific needs. Our universal metamodel is an extended version of the core logical metamodel we saw before. It supports two types of extension, sense classes in light blue and custom tab classes in green. The framework idea is that by specializing the mentioned extension classes, a concrete tool is defined, which provides new possibilities compared to the core platform. There are two types of specialization, simple for sense classes in blue and functional for custom tab classes in green. We'll explain the specializations with some examples. Sense classes are used to specialize textual and file logs sent from Workstation. These include literal with general sense that allows you to log a single value of things like runtime and accuracy, file with sense pointer for uploading specific types of files with whatever values are relevant, and literal with /pair sense, which lets you encode a pair of values that the core tool will recognize, split, and store. But the most important is functional specialization. You can write your own code that will be called with a single parameter, run ID or project ID, and the result displayed in a new browser window. For example, the loss graph. The program, when run, will in a new page graph loss values and epoch numbers taken from the corresponding run instance. A more complex example would be gold-silver view, which would take relevant test images and place them in a table next to gold and silver captions known and generated respectively. To have a presentable view of the current state of the training program that can then be shared with coworkers or end users. The table, as simple as it might seem, is very useful for sharing progress for this specific task and can't be replicated in Weights and Biases. There are multiple human actors related to our framework. This cooperation requires beforehand agreeing on some formalities for the smooth use of the platform. That is, the list of permitted role names and the semantics of these roles for messages sent from Workstation to the data server. Such extensive agreement should be sufficient for then developing the extension programs. We will call such an agreement a DSL memorandum. While an informal version of this is in place for the development of any DSL tool, ours covers a wider area, thus excusing such a term. This is a version of a page where the parts of the DSL memorandum relevant to the core framework would be passed to it. It's important to set this up so that afterwards the custom extensions are stored and called as expected. When this is done and the extensions are programmed, you have yourself a working specialized tool where you can create and view projects, track and compare information on different runs, as well as run your custom tabs to access your own specialized features that'll fit your deep learning data management needs exactly. Thank you for your attention. Any questions?